So there are many ways to describe the composition of a solution, and two of those you already know. They include the molarity, which is the moles per liter, and the mole fraction, which is the moles of one component over the total moles in the solution. So two other ways are the mass percent of the mass percent of a solute is just the mass of the solute over the mass of the whole solution, and then times 100%. And we also have the molality, which is symbolized by this little m, whereas molarity is the big M. So molality is the moles of the solute over the kilograms of the solvent. So now we're going to look at what happens in the formation of a liquid solution. So in terms of the energy changes, there are three basic steps. So the first step is expanding the solute. So you can see here, and the second step is expanding the solvent. So we need to expand them basically so that their molecules can mix together. Because if we just put this here, then they wouldn't mix because they're too clumped together. So expanding the solute and expanding the solvent make room for the interaction. And then the third step is the solute and the solvent mixing to form the solution. You can see that the molecules are now intertwined. So the first two steps, expanding the solute and solvent, are usually endothermic. And that's because to expand them, you have to break them apart, which involves, breaking those intermolecular forces, or if it's an ionic solid, you have to break those ionic bonds. And then the third step is the exothermic one, and it depends on how strongly the solute and the solvent are attracted to each other. Remember that when we have the electrostatic attraction, that creates negative energy. So the more attraction that the solute and solvent have for each other, the more negative the energy will be. For example, if they're both polar, the solute and the solvent, then the positive and negative ends will be attracted, and we'll have more exothermic third step. So as we know, nature likes the exothermic reactions. So this third step is usually, it has to make up for the endothermic steps 1 and 2. So we need the third step to be very exothermic in order for the reaction to happen. Or the other option is the first two steps are not very endothermic. Either way, when we add up all these three steps, the energy needs to be as negative as possible. And so the sum of the enthalpy changes for these three steps is called the enthalpy of solution. So that's what you're going to look at when determining if these two substances will form a solution. If the enthalpy of solution is very small or negative, then it's more likely to occur. Whereas if it's very high and positive, then it's not likely to occur. And another term is the enthalpy of hydration, which is just the steps 2 and 3. So the general rule is that polar solutes will dissolve in polar solvents, and nonpolar solutes will dissolve only in nonpolar solvents. We can't have a polar and nonpolar solute and solvent. So the reason for this is in the energy changes of these three steps. So as an example, let's look at NaCl dissolving in water. As we know, NaCl and water will both be polar because sodium chloride is an ionic solid. So step 1, expanding the solute. This step will be very large and very positive because we have to break those strong ionic bonds within NaCl. Step 2, expanding the water. will be large and positive again because we had to break the hydrogen bonds between the water molecules. And step 3, the interaction of the solute and solvent will be large and negative because the ions from the NaNCl and the polar water molecules are strongly attracted to each other, which creates that negative potential energy. So the third step, since it's so negative, it makes up for the large positive steps 1 and 2. And if you were to add up all these steps, the enthalpy of solution actually turns out to be positive. But it's only slightly positive. It's like something like plus 4 kilojoules. So the enthalpy of solution, even though it's positive, it's small enough that the process still occurs. So we're not really only looking for a negative enthalpy of solution, we just want a very small one. So for a nonpolar solute and nonpolar solvent, we have a similar story. So steps 1 and 2 will be positive, but very, very small. Since in nonpolar substances, there are weaker intermolecular forces, there are definitely not any ionic forces, so it's pretty easy to break them apart. And step 3 will also be very small and negative because the nonpolar substances do not have any attraction. So all 3 steps are very, very small, and so the enthalpy of solution turns out to be small as well. Whereas if we mix them, for example, a polar solute and nonpolar solvent, then step 1, expanding the solute, will be very large and positive because it's harder to break apart the polar substance. Step 2 will be very small and positive since it's easy to break apart the nonpolar substance. However, step 3 will be very low and negative since the polar substance and the nonpolar substance have a weaker attraction. So step 3 does not make up for the high positive step 1. So more factors that influence the solubility of a substance are pressure and the temperature. So Henry's law says that the concentration of a gas that can be dissolved in a solution is directly proportional to the pressure above the solution. So when we have more pressure above a solution, more gas can be dissolved. And the solubility of a gas in water also increases at lower temperatures. So higher pressure and colder temperatures, more gas can be dissolved.